For Chapter 9, we'll start with number 32, which is to propose a mechanism for the following reactions. So with this mechanism, we want to remember that our alkene is nucleophilic, and we have our acid, which is going to act as our electrophile, or in this case, a proton source. So we're going to have a proton transfer. And the proton is going to go to the hydrogen that has more hydrogens. On this first carbon here, carbon 1, there's 2 protons there, and carbon 2 has 0 protons. So the carbon that is richer in protons is going to get more. So we'll have our hydrogen goes here, and that's going to leave carbon 2 deficient. So we're going to put a carbocation there. We have a tertiary carbocation that forms, and this is water. That is the result of the loss of the H there. So our tertiary carbocation is pretty stable. If I go to carbon 1 where the hydrogen was placed, that would be primary, and on the other side is a secondary carbocation. So it's not going to shift there. Our water that was present can now do a nucleophilic attack at the carbocation. So that red H is still there, I just have not drawn it in just to simplify things. So water comes along with its 2 hydrogens, and it's now positively charged. And we can have another molecule of water pick up the extra proton. So there's another proton transfer to get that product there. So our arrows that were drawn here were a proton transfer. We had a nucleophilic attack and another proton transfer. So that is how you would do that mechanism. For B, we're going to start with the same arrow first, the proton transfer. Here I have a secondary carbocation, and that can become more stable at the tertiary position. So a hydrogen from here is going to rearrange to that carbon. So I have the hydrogen here, the hydrogen here, the carbocation is now there. This hydrogen is still here. You can draw it in or you don't have to. This is now a tertiary carbocation, which is more stable. So we just did a rearrangement. Then we have water present, which is our nucleophile that's going to attack the electrophile. You can do that up here as well, nucleophile. And then everything comes along with it. And then the last step will be a proton transfer. So any water around can just grab that hydrogen there, and we get the desired product. All right, here's another mechanism, same process. We're going to have a proton transfer first. That's a tertiary carbocation. Br minus was kicked off in that reaction there when we did the proton transfer. So the Br is now acting as our nucleophile. This is our electrophile. Get a nucleophilic attack here. And then we get the bromide. For each of these reactions, we're going to predict the major product. An alkene that's substituted, so we have an asymmetric alkene here. This is going to undergo a reaction with mercuric acetate and water, where water is the nucleophile. This is going to give us the Markovnikov product. Our carbon skeleton will be the same. In this case, the nucleophile, which is water, is going to add to the carbon that is more substituted. So our alcohol is going to add here. In the reaction with Br2, we have our carbon skeleton. This is Br2 plus water, so we're going to get the halohydrin. That's going to push the methyl group forward. We would get the OH here. And a Br would be trans to that. And then we'll also get the enantiomer. Hydrogen platinum is our reducing reagent. And that will reduce methyl group, and we'll get 2 hydrogens there. And that will be a syn addition. So if you want to draw the hydrogens in, you can. With HCl, this is also a Markovnikov product. The Cl will go to the carbon that is more substituted. And this would also form a new chiral center. So if you wanted to draw that dashed and this wedged, you could do that. Plus the enantiomer. KMnO4 plus sodium hydroxide, that is going to give us a diol. And that will be a syn diol. So if this was wedged, my alcohols would be dashed. Plus the enantiomer. All right, for 31, we're doing a couple more reactions here. Borohydride plus THF, H2O2, and sodium hydroxide. This is the anti-Markovnikov. We're going to get a cis product. And our alcohol, you can say that it's wedged. The OH is going to go to the less substituted carbon. This is the H. And that's how we would do that one. You'd get the enantiomer here as well. For Br2, we're going to get an anti-addition. So you get the anti. H2 platinum is still going to reduce. For HBr, this is Markovnikov. So our Br is going to go to the more substituted carbon. Which would be the carbon that's on the ring. So we get a Br here. And then if you wanted to draw in the H, you could do that. For RCO3 and acid, this is the peroxy acid, which first forms the epoxide. Get the epoxide, and then when we add acid and water, that will open the epoxide up. So we get the anti-diol. Here we want to look for reagents that will add or give us the products that are shown there. We have an alkene that's on the end, and here we're adding a Br, and what's not shown is the H that's here. Our product here is anti-Markovnikov. So we can't just add HBr. We want to add HBr with the peroxide to switch the regiochemistry. And then in the second one, our Br is at the more substituted. This is the Markovnikov product. So we can just use HBr here. With this alcohol, we have an alcohol going to the more substituted position. You can use H2O with catalytic H2SO4. You could also use Hg acetate with water and NaBH4. And here we're giving an alcohol on the end, or the anti-Markovnikov. So this will be the BH3, THF, and H2O2, sodium hydroxide. Here we are predicting the major product. This is the borane, so we're going to get an alcohol that is anti-Markovnikov, so our alcohol will form on the end. H2 platinum is going to reduce, so we'll get rid of all of our double bonds. And you can draw the hydrogens in here, or you don't have to. All right, this is the peroxy acid, where CH3 is the R group. So this is the same as RCO3H, followed by acid. So we're going to get the epoxide first, and then upon reaction with the acid, we'll get the transdiol. Osmium tetroxide with sodium bisulfite, we're going to get a syndiol. Get this one plus the enantiomer. This is acid plus water. We're going to get the Markovnikov addition of water. And the alcohol will go to the position that is more substituted, which is this one. HBr, same thing, it's a Markovnikov addition. The Br is going to go to the carbon with more carbons. So my Br goes there. Osmium tetroxide is going to form a diol that is syn. So if my alcohols were this way, that would make these here. And that's what we'd see for that one. All right, in this problem, we're looking to identify the reagents that are needed to make these transformations. For this one, we have a chlorine that's getting added to the more substituted carbon. So this would be HCl. On this one, we have a hydrogen, an alcohol that's dashed. There's also a hydrogen here that is dashed. This alcohol is getting added to the less substituted carbon. This is an anti-Markovnikov product. So this will be BH3, THF, H2O2, and sodium hydroxide. All right, here we're looking to eliminate a bromine by making an alkene, and reagents that we know how to get rid of alkyl halides, or the halides, is to use a base. And we want to use a base that will act as a base only. So we can use DBU. You can also use DBN or sodium hydride. Any of those bases would work here. We don't want to use T-butoxide. That results in the less substituted alkene. So no T-butoxide. So for this one, we're looking to do an elimination. And we know how to do that from Chapter 8 problems using a base. So you can use DBN. And that's going to grab a hydrogen that is beta to give us the most substituted alkene. That's going to be an E2 reaction. You can also use DBU or sodium hydride. You would not want to use T-butoxide though, because that's going to give you the least substituted alkene, which would be that one right there. So we want to stay away from T-butoxide. In problem H here, we're doing addition of Br to the more substituted carbon. This would be HBr. So with these, you just want to make an observation as to what is different in the functional group and then see how you can change it. All right, so compound A reacts with one equivalent of H2 in the presence of catalyst to give methylcyclohexane. So A plus H2 with catalyst, so we'll just call that PD, is going to give us methylcyclohexane. And compound A can be formed upon treatment of 1-bromo-methylcyclohexane So 1 bromo, 1 methylcyclohexane with sodium methoxide. So if we're doing anything to get a cyclohexane with A, we need an alkene here because H2 palladium can react with that. So sodium methoxide here is going to act as our base, and it's going to do an elimination here for A to be 1-methylcyclohexene. That's how you would get that one. Right here, we're looking for a synthesis of this compound. So a couple of things to observe here. We're doing an elimination. So we need to have a leaving group. We also need to shift our functional group location. Before it was at the tertiary center and now it has shifted over. And other things we need to do is to fix our leaving group because OH is a bad leaving group. Okay, so if we were to work in a backwards direction, in order for me to do an elimination here, I need to have a leaving group there. So I can put a leaving group here. And in order to get a leaving group there, I probably need to have an elimination here or a double bond there. And then that could be the result of a leaving group here. So this is pretty much like the alcohol over here. So if I'm going to go in the forward direction, I'll just do it on this side. I first want to make OH a better leaving group. So I can do the TS chloride here. So now that is a better leaving group. So then I want to do, if I go backwards here, this is my leaving group step. So that's step A. Now I need to get to step B. And that is to do an elimination, which hopefully would result in this double bond. So I need to use a base, a small one. So I'll just use sodium hydride. And that's going to get me the most substituted alkene. And now I need to make a leaving group at the less substituted carbon to do step C. So I can use HBr in the presence of peroxide. And that will put a Br here. And then I can use a big base this time because we want our alkene to be on the other side and not the more substituted, so I can use T-butoxide. And to get that product right there. Another step route that you could have taken is to do the elimination under acidic conditions. So if I did H2SO4 with heat, that would form the carbocation, and then I would do an elimination from there. And then you could do the next part. So the number of steps is maybe one shorter actually in this case. And this one would work if there's an alcohol there and you don't have to worry about a rearrangement. All right, here are some more synthesis reactions. So to go in the forward direction for the alcohol, I'm just going to go this way. I want to do the same thing where I make it a tosyl chloride. Here I would not want to use the H2SO4 in heat because my alcohol is on the primary and that could rearrange. So I'm going to put a tosyl chloride there. Then do the elimination. So DBU. So I'm going to get that one. And now I want to put the alcohol at the more substituted position. So I can use the mercuric acetate. To go in the backwards direction, this is the same process, tosyl chloride, to make it a better leaving group. And I would use DBU here, or sodium hydride, or DBN. And then once you get to this, we want to do an anti-Markovnikov addition of water. And so we use BH3 THF. And see here, we're getting rid of a chlorine, and that's pretty much it. So we don't have any reactions that make a chlorine go poof, disappear, and then leave in its place hydrogens. But if we look at the stereochemistry, we can see that the hydrogens are on the same side, which might make us think, hopefully, that it came from cyclohexane, where we added that. And we can get to cyclohexane if there was a leaving group there, which we have. So we can do an elimination of this product here. We've got an anti-coplanar hydrogen. We just got to use a base, DBU or DBN. That will do the elimination. And then we just use H2 palladium. Here is a mechanism. This is what we've seen at the beginning of this with a couple of the problems there. So we're going to do a proton transfer. My hydrogen's going to go to the carbon with more hydrogens. Carbocation goes here. And here we're showing the product. The OH is adding to that position here. So I think this methyl group is going to shift over there. So we have a rearrangement. So my carbon is there now. Here's my carbocation. We have H2O. Can attack where that carbocation is. Everything comes along. And then we have a proton transfer. From any water that is around. So our arrows here were proton transfer, rearrangement, nucleophilic attack, and a proton transfer. Here's looking at more reagents to make each of these. Here we're going from methylcyclohexane to methylcyclohexane. So we're adding hydrogens. This H2 nickel is another catalyst that you could use. Here we are adding an OH and a Br. The OH is going to the more substituted carbon, so we can do a halogenation, which is Br2 H2O, a hydrohalogenation rather. In this particular one, we're opening up the ring. So we have 6 carbons and a methyl. Here's our methyl. So this is 1, 2, 4, 5, 6, which is the resulting of cleaving there. This is O3 DMS. And here we're adding a hydrogen and an alcohol on the same side to the less substituted position. This is BH3. And then here's another couple of problems with figuring out reactions. We're starting with this external alkene on the cyclopentane ring. For that first one there, we're just cleaving. If you notice here, we're gaining an oxygen and losing that. So we're just cleaving that. So this is O3. To add a Br to the less substituted position, this is HBr with peroxide. If we want to add an OH there, that's BH3, GHF. In this one, we're adding 2 alcohols to this carbon and this one. So that could be a diol. You can use OSO4 and NMO. Because the stereochemistry here is not indicated, you could also use RCO3H followed by acid. So that's another way to do it. Here we're adding OH to the more substituted carbon and then Br, so this would be a Br2 plus water. And then we also have an OH on the methyl group here. We're adding an OH to the less substituted carbon. This is a tertiary center, so I'm just going to use acid and water. But because it's tertiary, I don't have to worry about a rearrangement. That's why I'm using acid and water, but if there's a concern of rearrangement, you would certainly want to use the mercuric acetate. The last problem here, we're just looking at the bromine on the more substituted carbon. This is HBr. So this structure is A here, that's A. And if I want to make it back into a different alkene, use a small base, this is NaH, to do the E2 reaction. Then to go from cyclohexene to cyclohexane, this is H2. Another syn diol here, I can use KMNO4. With base. And then the anti-diol, then that's when you want to use the RCO3H. Plus acid and water.